Epoxides are synthetically useful because we can take an alkene and we can generate the epoxide and then ring open that epoxide to generate a variety of products. Epoxides are susceptible to ring opening by nucleophilic attack, so we can use any good nucleophile to open this epoxide ring. This is just a simple SN2 reaction where the epoxide attacks, opens up the ring, and then after an aqueous workup we can reprotonate the alkoxide to generate an alcohol and a newly installed nucleophile. In the case of an asymmetric epoxide, the nucleophile can either attack either side, so we can end up with the nucleophile on the right or the nucleophile on the left. But if these two sides are substituted differently, the nucleophile will attack the least sterically hindered site, just as in a standard SN2 reaction. So in this last reaction we have a tertiary site and we have a secondary site. SN2 reactions, because of backside attack, cannot attack a tertiary site. So the nucleophile instead will attack the secondary position, opening the ring this way, and we install the nucleophile at the least sterically hindered site. This is regioselective. Ring opening reactions can also be acid catalyzed. This will generate a hydroxyl group and addition of a nucleophile. In this case it's going to be a halide. So to go through the mechanism, we can first protonate the oxygen, kicking off the halide. The halide is now available to do a backside attack and open up the activated ring. This will give us our product. In the case of a tertiary epoxide, we can actually use acid catalysis to reverse the regioselectivity. So if you recall, with a standard nucleophile, the tertiary site will be unaffected by the nucleophile. The secondary site will be attacked. But if we have an acid catalyst, we'll actually get the reverse, where the nucleophile, in this case the halogen, will actually add into the more sterically hindered site. Why does this occur? Well, let's take a look at our mechanism. First, we protonate the oxygen. After the oxygen is protonated, we have an activated ring. If you consider the resonance form of this ring, we actually break this bond and we generate a carbocation. A tertiary carbocation is relatively stable, so in a tertiary substrate, in a tertiary epoxide, it is possible to generate this carbocation, which is more susceptible to nucleophilic attack because of its positive charge. So in the case where we generate a positive charge in this ring, the nucleophile will attack the more sterically hindered site and then ring open the epoxide to give us this more substituted product. To summarize, epoxides can be ring opened using nucleophiles, which allows us to install a wide variety of functionalities to a carbon atom. Nucleophiles will always attack the least substituted carbon in these examples. We can also ring open an epoxide under acid catalyzed conditions, and if we use these conditions, we can force a nucleophile to attack a tertiary carbon instead of the least substituted carbon. So essentially, acid catalyzed reactions will reverse the site of attack.